this video covers how we can take our constant acceleration equations that we learned previously in the semester and apply them to angular kinematics. So here are 4 different linear constant acceleration equations that we learned earlier in the first semester. And we can manipulate them by taking our linear variables and changing them into our angular kinematic variables. So instead of v equals v naught plus a times t, we're going to have omega equals omega naught plus alpha t. We essentially just take the original equations and replace the velocity with the angular velocity, acceleration with angular acceleration, and displacement with angular displacement. And we develop these equations. So let's try using these equations in a problem. A disk initially rotating at 40 radians per second is slowed to 10 radians per second in 5 seconds. Find the angular acceleration and the angle through which it turns during this time. Alrighty, so let's look at some of the variables we're using in this equation. 40 radians per second is going to be our initial angular velocity, or omega naught. 10 radians per second is going to be our final angular velocity, or just omega. And 5 seconds is time. So we have omega naught, omega, and t. So let's solve for the angular acceleration with this equation. So we have our known variables, we can plug them in, and we find that the angular acceleration is -6 radians per second. So next we need to calculate angular displacement, which we can use any of the equations to do this, but I'm going to choose to use this one. So I can plug in my known variables, and when I solve, I see that the angular displacement is 125 radians. Great. Now let's do another problem. A grinding wheel of radius 0.5 meters is rotating at 14 radians per second when it undergoes an angular acceleration of 5 radians per second squared for the next 3 seconds. So let's label our variables. 0.5 is the radius, 14 radians per second is the initial angular velocity or speed, 5 radians per second squared is the angular acceleration, and 3 seconds is the time. At first, we are going to be looking for angular speed. So we can use this equation here and put in our knowns from above, and we see that the angular speed, or the final angular speed, is 29 radians per second. Next, we want to find the angular displacement. So we can use this equation. When we plug in our known variables, and we see that the angular displacement is 64.5 radians over this time. Now let's expand this idea a little bit more by calculating the final linear speed, which is just the radius times the angular speed. And when we plug in our radius and our calculated final angular speed, we find a linear speed of 14.5 meters per second. And finally, we can calculate the centripetal acceleration 0.25 meters away from the axis of rotation by using our centripetal acceleration equation. We can plug in our variables, and we see that that is equal to 210 meters per second squared.